Hello, everybody. Welcome to our Gen Chem Study Session number 2. Dr. Taylor, I'm going to go ahead and get started.
Fantastic. So the nice thing is now that y'all have done one exam under y'all, there's a lot of the general questions we had last time that we likely won't need. But again, if you have questions, let me know because there's lots of different things we can potentially talk about. I'm going to go ahead and for a moment go over to the announcements page of the 701 section because it has things like exam 2 reviews, which granted, this is one of them, but also has things like the exam 2 content. So a reminder that we are, I'm going to copy this over, doing sections 4.6 and 4.7, which apparently can't do 4.6, 4.7, chapter 5 and chapter 6 is pretty much where we are. There are a few things that we don't do in chapter 5, like there's no lattice energy. So it's whatever we were doing in class, no lattice energy. And in chapter 6, there's no calculation of percent ionic character or calculation of dipole moment of dipole. In general, chapter 5 is where the calculations are. In chapter 6, the only real calculations you should be doing are either for bond order or are for counting electrons. So there are calculations in 6 as long as we count things like adding up all your valence electrons in a molecule. So, but that is I'm pulling off of the announcements page of the 701. What else was in here that I wanted to check on? So the other thing that is actually hanging out in the 701 section is for back for exam 1, someone had asked what end of chapter questions do we need? And I was going to see if I could copy those over, but I think perhaps there's too many things. Sorry. Basically, which end of chapter questions might we need for this upcoming exam? And that one you can also find. You just got to scroll back a little bit farther. So there's all kinds of lovely, wonderful things in the announcement section of the 701 section. So you guys might check that out. But there are things for exam 1 and exam 2. You will still get a periodic table. I need to double check with Dr. Diekman. Your potentially useful information might very well be exactly the same as it was on exam 1. There might be a small change to add percent composition, but that would be about it. So for those of you that were asking things like, do we need to memorize all the polyatomic ions? Yes, you do have to memorize all the polyatomic ions. Yes, you do. I know it's a lot. It is. But you can do it. You can do it. So a general reminder that when you're doing the exam, all work, all short answer work goes on the back of the Scantron. I had people who lost points either because they did not get to copy all of their problem of the short answer onto the back, or I also had some folks that just gave the numbers or just gave the answers. If it's a calculation question, we do expect especially to see work on those. So people lost some credit just because they had beautiful correct answers, but that's all they had. They lost points. So we do expect to see some amount of work on short answer for those. So just keep that one in mind. So what I'm going to go ahead and do is I had some folks ask me some questions actually in my class earlier today to make sure that we covered. So even though to me it always seems a little bit strange, we're going to go ahead and I'm going to do a Lewis dot structure of something particular, and we'll see what conversations we come up with. Draw the Lewis structure for the phosphate anion. So first of all, I have to know what that is. So from memory, phosphate, so it's going to have more oxygens, so it's PO4, -3, this is phosphorus. If I look on a periodic table, phosphorus is in group 5A, so it would have a -3 charge. So if this was just phosphide, it would have a -3 charge. Phosphate also has a -3 charge. So that's how I remember that. Then I'm going to keep scrolling back to my periodic table. Although we just saw phosphorus was in group 5A, so it's got 5 valence electrons. Then I have 4 oxygens. Each oxygen has 6 valence electrons. And then I have this -3 charge. So I'm going to add 3 more electrons for the negative charge. So I have a -3 charge. So therefore I'm going to add 3 electrons. Each electron is negative. I get to add 3. Also, for those of you who can see me frantically looking back and forth, I told my class this, and honestly, it's true. Whenever I am doing Lewis structures in front of a group of people, I actually use my calculator to add up all the electrons. That is because if I'm not careful, I will make a relatively silly math mistake, and then I will have done the entire structure wrong, and nobody wants that. I don't want that. You don't want that. So I will often go ahead and use my calculator to add up electrons because that makes my life a little easier. So that's also why I'm like, I think there are calculations in chapter 6 because I'm going to use a calculator to add up my electrons. So 32 electrons to put in this whole thing. So let's go ahead and get started. So I've got a phosphorus and I have oxygens. I'm going to put the least electronegative atom in the middle. That is going to be phosphorus. It's farther away from fluorine. Also, oxygen is very electronegative. So I'm going to put the phosphorus in the middle, oxygens to the outside. Also, in general, symmetry is typically preferred. So the notion that the oxygens are going to go to the outside should make sense. Every atom in here has to be connected. So I'm giving those all single bonds to get started. I just placed 4. So I'm going to take away 8 electrons, going to give me 24 left over. So this is -8 in bonds. My next step is to fulfill octets. I'm actually just going to use my little marker here. So I can go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Minus 24 electrons in pairs. None left over. So right now, I have a structure that at least has all of my valence electrons in there. So I'm putting that brackets on that -3 charge to remind us that it did go ahead, that the whole thing is an ion. So it does, the whole thing has a charge. Now I want to go ahead and think about octets. So all of my oxygens look the same right now. So if I highlight everything in there, this oxygen is sharing 2 electrons with the phosphorus, then has another 6 electrons to itself. So that does have has a full 8. Then I want to think about my phosphorus in here. And my phosphorus has a grand total of 4 bonds, each with 2 electrons each. So my phosphorus's octet is also satisfied. So right now I have a structure where my octets are satisfied. I know I did not do every single oxygen, but if you look, every single oxygen is identical. Every oxygen has 1 single bond and 3 lone pairs. So every oxygen is the same. The one in yellow is fine. They're all fine. So next up, then what I actually want to do is formal charge. Formal charge. So for formal charge, I'm actually now going to pretend that this oxygen and this phosphorus are going to basically split that bond And I'm only going to care about if the oxygen was going to separate from the phosphorus, what would it take with it? And what's going to take with it is going to be valence electrons. So it started off with valence electrons. Then I'm going to subtract essentially half of the electrons in bonds, which essentially will just be the lines, minus all electrons in lone pairs, which are dots. So for this oxygen, that is 6 electrons minus 1 for the line, 1 minus 1, 2, 3, 4, 5, 6. So my oxygen has a formal charge of -1. So each one of those would actually be the same. So I'd have a -1 since they're all the same. -1, -1, -1. My phosphorus here in the middle has 5 valence electrons, has 4 lines going to it, has no lone pairs, has a +1. So one of the things that I can see is because I have positives and negatives in the same structure, I should try to make the structure better than this. It's entirely possible that this is the best we can do, but I need to check, I need to see. So one of the things I'd like to do to lower my formal charge is to go ahead and share more electrons. But before I do that, since phosphorus is at 8 right now, I need to see if that's possible. So what I'm going to do is I'm going to go back to my periodic table, and I'm going to draw a big old line right here, right there. Because as long as I'm in the 3rd period or below, I can have an expanded octet. It does mean that I'm violating the octet rule. I'm going to have more than 8, but phosphorus is absolutely below that line. So phosphorus can have more than 8 electrons. What you might also notice is oxygen is above that line, so oxygen can't, but phosphorus below the line can. So because of that, and actually I don't have a choice, I'm going to go ahead and share another lone pair from the oxygen to the phosphorus. Since I have these two circled, actually the first thing I'm going to do is I'm going to redraw this because this is colorful enough as it is. So that way we can try this again. So I have a phosphorus in the middle, and I'm going to put in all my lone pairs in just a minute. I'm going to put that in. So right now, I have, eventually I'll get lazy. Maybe not. I should be nice and always draw in all the lone pairs. So right now I'm just trying to copy what I had before. Right now, the only goal is to copy what I had before. Okay. Because now all we're going to do is, since this is what I had before, less colorful, I realize. Now what I'm going to do is I'm just going to share one more lone pair. So since all the oxygens right now are the same, it doesn't really matter where it comes from. I'm just going to nab these. I'm just going to put a little arrow there. And so I'm going to have a brand new structure. So I am going to redraw this. For those of you on other devices, you don't have to. Oxygen, oxygen, oxygen. Lone pairs. Oh, there we go. It's like, where was my thing that made it easier to draw lone pairs? There we go. And we'll go ahead and still draw everything in brackets. Give it a -3. So always was move electrons. So we should still be okay on formal charge, or sorry, on octet. But I do want to recheck my formal charge. So now I have 2 different kinds of oxygens. So this one that I've just circled in red, 6 valence electrons, 2 lines, 4 dots, 0. This one down here at the bottom, which is what everything else will look like, 6 valence electrons minus 1 line minus 6 dots for -1. And then the phosphorus in the middle has 5 valence electrons minus now 5 lines, still no lone pairs, for 0 formal charge. So what we should hopefully see is, in comparison to where we started, I still have some negatives. So I didn't get rid of those. So I've got a -1 for this oxygen down at the bottom. That means that I actually have 2 more with that same formal charge because those 2 are all the same. So I'm just going to highlight those real quick. So this guy is the same, and this guy is the same, and this guy is the same. So all of those will actually have a -1 formal charge, because they all have the same number of bonds and the same number of lone pairs. So all 3 of those will be identical. But the one that has a double bond will be different, and the phosphorus, because it now also has a double bond, will be different from where we started. So originally I had that phosphorus on the right also had a -1 charge, and my phosphorus had a +1 charge, and now they're both 0. So usually this is a good place to say, aha, this is probably better than what we had, because I do have more zeros. So usually this is a pretty good place to stop because I got zeros. But I know you're curious. So I'm actually going to go one more, because one of the commonly asked questions is, but what if one double bond is good, maybe 2 is better? This is definitely my dad's philosophy when it comes to a lot of things. If 1 is good, 2 is better, right? So let's see. Let's just check and see. So I'm going to try to put this beside it. Put my phosphorus. So I already have 1 oxygen with a double bond, and now I'm going to just take them, I guess, from the top. I don't know. It doesn't matter. And again, I did pick this example on purpose so that I could talk about it for a long time, so that as y'all join the call, you can put questions in the chat. But this will take me a little while. And it did. People asked me for this in their review specifically. Well, we're getting there. We're getting there. So formal charge. This oxygen is still the same, 6 - 2 - 4 for 0, which means this one now that also has a double bond, and for electrons in lone pairs, or 2 lone pairs total, also 0. This one down here at the bottom should not have changed, along with this one on the left. So this should still be 6 valence electrons -1 electron in a bond -6 for the lone pairs, which is -1. So it's also -1. And I was going to check on that phosphorus in the middle and see how we're doing. 5 valence electrons -1, 2, 3, 4, 5, 6 for a -1 charge. So this one essentially at first glance looks like it's the same, because I still have 1, 2, 3 -1 charges, and I've got 1, 2, 0 formal charges. So at first glance, this actually looks like it's about the same as the one we drew before, but it's not, because before I had the oxygens were carrying the -1 charge. Now I have 2 oxygens carrying a -1 charge, but I have a phosphorus carrying a -1 charge as well. So now we have to ask ourselves a question, which is more likely and which is more stable, for basically phosphorus or oxygen to carry a -1 formal charge. Which one's better? Because that's the difference in between the 2 structures. The actual number of the formal charge is the same, it's -1. We've got a couple of those roaming around the molecule, but which one's more likely? To figure that out, we're going to go to a periodic table and basically look at which one's more electronegative. So I've got an oxygen here and a phosphorus down below. My oxygen is more electronegative. Oh, cannot write that very well, but that's more electronegative. Than phosphorus. So that oxygen is more electronegative than phosphorus. that means it wants the electrons in the bond more. So if I'm trying to think about what's the most stable configuration of my electrons in the molecule, giving the formal charge to the more electronegative atom is a better idea, is a more stable representation of the molecule overall. So when we go, that's the one that we're going to assume is more stable. So we are going to basically call this one less stable. It still is a valid Lewis structure. It has the right number of electrons. There's an attempt at formal charge, but this one is actually less stable. And this one, where I have 3 single bonds and 1 double bond, is more stable, more better. But so by formal charge, we're going to take this one. So what we have just managed to review is drawing Lewis structures from scratch. I know I did it quickly, but did it. We can do more of it if you want. Octet rule, formal charge. So drawing, octet rule, formal charge. That's what we've done so far. I have another problem though. We're not actually done yet. So right now I have 3 oxygens that are equivalent and 1 that's different. And the real question is that really the way that this works? The answer is no. So we have to introduce a concept. And what I'm going to do is I'm basically going to go ahead and show you what we would usually do. We would go ahead and draw resonance structures. And this one takes me a minute because Lewis structure simplifies. So what we're going to do, and I'm going to do this quickly. So right now I have this one. I know I need lone pairs. I'm not done yet. This is why Dr. Diekman draws lines instead of dots. This one right here. And we draw this cute little double arrow. That's what that's supposed to be, a double arrow. And look at that. Now drawing the double bond to the top. Now I understand that since all of this is in black and white, it very much looks like I just rotated things around. So in a perfect world, I would actually have done this, where we're going to make this one blue, and we're going to make this one green, and I need a different color, but I'm on a Mac, and we highlight this one down here pink. We make it look weird. This is highlighted pink now. Sorry, trying to observe the folks that are red-green colorblind. And one of those I left alone. This is pink. This is green. This is blue. So the idea is that they are different oxygens. I am actually drawing a double bond from the phosphorus to different oxygens, even though they all look the same. What I'm doing is I'm displaying the idea that my double bond is not just in one place. So weird. This is, I'm gonna keep going. So I know that y'all get the idea of, and now we're just gonna keep drawing them to the last place. But the point I actually want to make about this is, on the exam, if it asks you to draw a valid Lewis structure and it has resonance, you need to draw all the resonance structures. So while yes, it has taken me a little bit of time to draw all of the resonance structures, that's what you get to do, is draw all the resonance structures if that's what is called for or what is asked. Also, what I do want to also show you is I've got the double bond to the bottom oxygen, to the left oxygen, to the top oxygen, to the right oxygen. So I would also say that this has four for resonance structures. The double bond to each individual oxygen. Now, the reason why we say the Lewis structure kind of simplifies is because really that double bond is actually in all of those places at the same time. If you actually do some looking on various websites, what they'll actually draw for you is this notion of like half bonds. So the thing is this is more of what reality is basically is the double bond spread out. And for those of you that may be looking at various things on the internet for Lewis structures, you might have already seen this, where you have this kind of like weird dash line for part of the bond, and those are resonance. That's another way to demonstrate resonance. But what you might notice is you don't actually see me going ahead and putting the rest of the lone pairs, because that gets really tricky and really imprecise, essentially. And that's really not how we draw Lewis structures. It's another way, though, to say, hey, this has resonance, and that bond isn't really just in between one phosphorus and one oxygen. It's actually everywhere. The other way we can talk about this same idea is we can actually do the same thing with the concept of bond order. So when we do bond order, what we're going to look at is the fact that I have a single bond, a single bond, a single bond, and a double bond, number 2. So I'm going to basically add up all of my bonds and divide by the total number of locations of bonds. Basically, I add up types of bonds, and then we divide by number of bonds. The reason why I struggle with this is because bond order in your textbook is linked to molecular orbital theory, which is very cool, by the way. I like molecular orbital theory. But that's not how we're going to use it. We're going to use it to demonstrate the fact that really the bond order here should be 5/4 or 1 1/4 or 1.25. So I don't have single bonds and a double bond. I actually have 4 1.25 bonds is what I have. So I have 4 bonds that are not single bonds and are not double bonds. They're actually 1 1/4 bonds. So that's what is real, is I actually have 4 bonds that are all identical. They are 1 1/4 bonds. This is the idea of resonance, that I actually have 1 1/4 bonds. All bonds equal. And this is part that's weird about resonance, is resonance in nature, all the bonds are the same length. So we're trying to describe what we see in nature, which is that all of the bonds actually have the same length. But this idea is strange. So this is a good example of us as human beings draw Lewis structures to understand the world better. And then the world is a bit more complicated. And so we basically try to band-aid our original drawings so that we can make meaning out of what we have left. So there's lots of different ways to talk about this. A couple of things to keep in mind. Part of the reason why this problem has taken me almost a whole half an hour to do is because for our class, we are going to draw a valid Lewis structure, check octets, then check formal charge, then look for resonance. That is supposed to be the number 4. 4. Then look for resonance. So this is the order of operations. We do resonance last and on purpose. We want you to worry first. Are you drawing a valid Lewis structure? Do you have all the atoms connected? Did you add up all your valence electrons? Did you take into account the charge correctly? Did you double check for octets? Did you make sure all the octets were satisfied? Did you check for formal charge? Did you make sure that you drew the best structure that you could with formal charge? And then at the very end, once you've satisfied everything else, then you can look for resonance. So this is something to keep in mind. That's what we expect if y'all are doing it on your own. If y'all are doing it on your own, we expect you guys to do that in this order. Your textbook and definitely the internet will have different expectations and may very well present you and be like, these are resonance structures, ta-da! And formal charge may or may not have been optimized if you are presented with them. So I did an example in class today that I think most of the instructors do. And that is to look at formal charge with really specific sets. And you could actually call all of these resonance structures, even though they're going to have different formal charges, and you can definitely choose the best one. Since the right number of electrons are here, you can describe all of these as resonance structures of each other, but you have to keep in mind, if we are asking you to draw things, we expect this. We expect you to draw a valid Lewis structure, check octets, check formal charge, and only after you've optimized everything, then you're going to look for resonance. But you will hear it used in different ways because it has a broader definition, but because y'all are learning to do Lewis structures yourselves, we're going to do it in this order. Valid Lewis structure, check octets, check formal charge, and then at the very, very end, then we can do resonance. Okay, so I'm going to take a drink, and then it's time to see if we have questions.
Okay. Yes, ma'am, we do. We have a lot, so you bear with me. So if you have electrons left over, would it go to the p element? Can you go over resonance, percent composition, calculations, bond order, molecular nomenclature, isoelectronic ionic radius, ionic bonding, molecular/formula mass? Now, some of those were already answered, but when
I missed.
writing
Hold on. I missed something. I missed something after radius.
Ionic bonding, and molecular/formula mass.
Got it.
When writing empirical formulas, do we need to know the exceptions that shouldn't be reduced for the exam? I think what my lab taught me was mercury 1 and peroxide. So I think I got that right. If you have any tips, do you think it would be better to memorize the ions in chart form / the way the chart presents them? If possible, can you give an example of how we might need our knowledge of the ions chart for the exam? When it comes to, sorry, give me a second. Okay. When it comes to octets, what elements does it apply to, and what are good ways to check for octets in Lewis structures?
Okay.
Is resonance the deciding factor of a Lewis structure is valid? Deciding factor if a Lewis structure is valid, or is the best structure, or does it depend on the question?
Okay.
If the proctors are being disruptive during the exam, is there anything we can do? Can you explain which elements are able to have an expanded octet?
Okay.
Can you do an example of ranking bonds from least to greatest ionic character? What does that mean as well?
Okay.
When given names of compounds, how do you know which ones are covalent compounds? Drawing the Lewis structure. Can you help with understanding electronegativity trends versus ionic character, as well as ionic radius versus atomic radius trends? We use the periodic table for all of these, correct?
Yes. Okay.
Yep. And then, what was wrong with the Lewis structure in which you had two double bonds? I didn't catch the explanation.
Okay.
Could you explain the type of questions that could be present from memorizing the polyatomic ions and the percent of those questions that will be present on the exam?
Okay.
Can you do an example of the type of equations that will be on the exam? And I believe that is all for now.
Cool. So let me address the one with the proctors first. So, yes. Also, I want to know about this now. I actually wanted to know about it 3 weeks ago, but since what we have is we have now and we have the future, I want to know now. I don't, so because basically, if you currently know that your proctors were being disruptive, I need to know about that today, because when we therefore assign them where they're going to go, I can make certain either that they're reassigned, or I can make certain that they're basically have a talking to, because essentially, otherwise, what can happen while the exam is going on is there's usually some instructor that is supposed to check on that room. You can always basically tell the instructor. You can also raise your hand and tell the proctor. Frankly, you can absolutely raise your hand and be like, you are being too loud. So you can do that too. The thing, I know what was told me, email me like right now. My net ID is the fastest way to do this. 0310000 at UT Dallas. Do remind me what room you were in. .edu. Or at least I'll have your last name and I'll double check what room that was. I will say there's a chance that it was my rooms. Also, just a chance it was me, because one of the things that I know was happening on the first exam is I had a lot of TAs who had never proctored before, and so they were very concerned with getting things correct, and I had to come in and correct them while the exam was happening. I have a couple of different things that I'm going to be doing in the rooms in green so that will be less than it was. That's really all I can guarantee, because they are first year graduate students. They are learning how to proctor. Some of them are naturally better at it than others. Some of them are not brand new. But I do want to know about that, because I know there were problems in the rooms that I was in charge of in green, and I'm going to move some folks around because of that. I'm also going to move a little bit of the furniture around to help with that. So I have a couple of things that I'm going to be doing to make the rooms better. But I want to know about that, and I want to know now, so that I can make sure it gets addressed, because I only know about the rooms in green. And for those of y'all that were in green, you probably know that you saw me for like 5 minutes every like 20 to 30 minutes, because I'm actually bouncing between 4 different rooms in green and walking in between them. And depending on how things were doing, depending on how often I was there. So one of the rooms in green, y'all barely saw me at all because it looked like that room was okay. So if you're talking about something over like an ECSS, then I don't know about it at all. So let me know and we'll get on that. But in general, there's an instructor that's walking around in between the rooms. And you can flat out, I know it's hard, but you can tell the proctor raise your hand and be like, you are being loud, can you please be quieter? Because that is a real concern. So tell me, let me know. We'll do our best to fix it. Also, if it was me, I am sorry, but you can still tell me that, by the way. You can flat out tell me. Because some of the rooms in green did not run like I wanted them to, and I was trying to fix it, and that sometimes was not as quiet as it could have been. Okay. Things I want to do now. First of all, I want to talk about the questions that came up about what we just did. So one of them was to talk about the Lewis structure that had the 2 double bonds. So going back, so the only reason why we didn't like this structure is because the phosphorus is carrying the -1 charge, and phosphorus is less electronegative than oxygen. So because of that, it's less likely to carry the charge. So not as likely to have a -1 formal charge. It's supposed to be the -1. So that was really the only reason why we didn't like this one, is because since there is a choice to make between the phosphorus and the oxygen, we want to go ahead and make the choice of which one is more likely to carry a negative charge and make that consistent when we can. So that's where that one came from. I got that one. If we had electrons left over, would we have just put them on the phosphorus? Yes. So I actually was doing an example. Let me just do another example real quick. So I did an example in class, and I'll be straight up. I grabbed this example from Dr. Diekman's workshop on Friday because there were extra copies of it hanging around. And so I was like, oh, look, Dr. Diekman has a whole workshop with a bunch of Lewis structures. Wonder what he used. I'll just grab these. So this has 8 valence electrons for the xenon. Let me grab a periodic table. Let's do this the right way. I am going to make this smaller though, so you might just have to trust me on where those are. There we go. So xenon, whoa, xenon is way too close to my scroll bar. There we go. There's xenon. Having a good time. So xenon has 8 valence electrons. Bromine is going to have 7. So 8 plus 4 times 7. That is 8 plus 28, which is 36. 36. Xenon's going to go in the middle. All the bromines around it, because the bromine, we're going to assume it's going to be more electronegative than xenon since it's halogen. Bond everything together. That's 8. I have 28 left over. Whatever. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Minus 24. I have 4 left over. How bizarre. But since I have 4 left over, they absolutely go on the xenon. And they can go wherever you want. The goal when you put lone pairs on the central atom is to try to draw them somewhere where it's clear they're on the central atom and that they're not part of the bond. So since I have 2 pair, I usually draw them opposite each other. But if you want to like make it like it's a hat, or if you want to make it like a little feet, like whatever you want, as long as they're somewhere on the central atom. But yes, so if you have extra lone pairs at the end, they do go on the central atom. So yes, if there are electrons left over, they go on the central atom. Correct. Let's So I think I already answered this question about resonance and valid Lewis structures. But let me go ahead and show you the place where I think we've already done that. So whenever it says draw a valid Lewis structure, this is really just placing all the valence electrons. So when we say valid Lewis structure, a valid Lewis structure just means that it has the correct number of valence electrons. That's shown. That's the reason why we always count those first, is that's actually the valid part. Checking octets then is to make sure that every element is sharing 8 electrons, unless it's one of the weird ones, but you're still going to check. I'll show you my slide for that in a minute. And then formal charge and resonance goes last. So resonance is the very last thing you do. And it is separate. It is separate from everything else. So these are all things that can happen individually. So you can have a valid Lewis structure. Well, checking octets and valid Lewis structure really go together. But you can absolutely have weird formal charges that are valid. You can also have things that, yeah, so in this order, resonance goes last. The thing I wanted to show you, did I get rid? Nope, there it is. PowerPoint. Yay. So this is my favorite slide, partially because I made it. I made it over an old periodic table, you can kind of tell. But basically, what it shows is that third period and below is the expanded octet. So someone had asked, where's my expansion? Or what elements can handle expanded? You literally just draw a line after the second period. So it's third period and below. So silicon, phosphorus, sulfur, chlorine, all can do expanded octets. So third period, silicon, phosphorus, sulfur, chlorine, and below, expanded octet. Boom. So below the line can be expanded, needs to have at least 8, but can be expanded. Above the line is 8 and some of our wacky exceptions. So in yellow is carbon, nitrogen, oxygen, fluorine, and neon. Those get 8 valence electrons and only 8. Then we have our exceptions, which are boron, which can have 6, beryllium, which can have 4, hydrogen, and helium that only need 2. Lithium does get to act like a metal. So lithium's over all by its lonesome. So there's our sets. There's a lot of exceptions in there, you might notice. Lots of exceptions, but there are in fact a set that get 8 and only 8. And there's a set that usually have 8 but can have more. So that's the other kind of game to play, is there's a set that can have 8 but could have more than 8. And that's that expanded octet in the third period and below. Okay. So I think we talked about elements and their octets and expanded octets. Do that one. So a lot of things came up about polyatomic ions. So let's talk about some polyatomic ions and some general tips that I have. So also for exam examples, technically I started off with something that could be an exam example because it said draw the Lewis structure for the phosphate anion. So that like half hour we spent with phosphate actually started with naming it by name in words with no formula. You'll get a different answer if you draw the wrong thing. So people are asking for things like percentages. I can't tell you, and this is for 2 different reasons. One, I haven't finished looking at all the questions on the exam yet, so I don't know. Also, even if I remembered from working on it earlier today, we might change it because all 4 instructors wrote 7 or 8 questions and we tend to cut a few down. And actually the last reason is even worse than the I don't remember, which is I rarely notice because I read phosphate and I know what that is. So honestly, you don't want my answer. You don't want me to guess because I'll guess wrong. And I'll guess too low because there are times where I see that the word is written out, but again, I've been teaching this class now for over a decade. Oh God, that makes me feel old. And I don't always see the fact that the formula is not there because I know what that is. Extra true because when you talk about phosphate and you talk about things like a ribose phosphate backbone in DNA, that's the phosphate. This compound is the reason why DNA usually has like lots of magnesium positive ions around it. Is DNA is a really massive negative molecule because of all the phosphates. So phosphate especially, I know real well. So yeah, so I can't actually take a guess at what percentage polyatomic ions are there, partly because we're not done editing yet. So whatever number it's currently at, it might change. And then the other reason is I would not notice. I know it doesn't really help you, but that's what I got. So some tips and tricks. I'll go ahead and put it up again because it's honestly not bad. I can't hide the fact that I don't like this. This one. So on one hand, I can't hide the fact that this is really not my favorite thing ever. But there are things like this. So this is Nick the Camel ate a clam supper and crepes in Phoenix. And what this is supposed to do is this is supposed to help memorize all of the polyatomic ions that end in ATE. And this can work. So to give you an example, so it's Nick the Camel. So it is actually on my next slide in here. So I'll put this up if you guys want to, when you guys look at the video back again, you guys can take screenshots. But the way that this works is you have to spell everything correctly. But then what's going to happen, I'm going to use the word clam this time, just for funsies. So one of the words in here is the word clam. So first of all, because of the Cl, this is for chlorate, because all of these in here are for the ATE endings. Then in the word clam, there is one vowel. So that tells you it's a -1 charge. And then there are 1, 2, 3 consonants. Consonants. No, wait, that's not the plural. Consonants. So 3 oxygens. There's your chlorine, there's your oxygen, there's 3 of them, a -1 charge. Now, perhaps as is obvious by the fact that I was having problems spelling the word consonants, because this method is based on spelling, if you can't spell this sentence, this doesn't help you. And then at that point, I don't know the answer to this. I don't know if you're better off learning or memorizing how to spell all the words in the sentence, or if you're better off learning and memorizing the polyatomic ions in a brute force way. I honestly don't know. That depends on you and your brain. And I don't know what's better. Y'all just saw me have problems spelling something, so you can likely then figure out why I'm not a big fan of this. Ironically, I was super good at spelling when computers were worse at it. Also, when I was in English class in high school and I got tested on spelling and things like that. So, but this is an option. Since it's obvious that this is not my favorite, it can be yours, by the way. I will not look down on anyone who uses this. I will not. I just, it's not ideal for me and my ability to spell things. Here's what I actually do. What I actually do is I look for patterns because I love patterns. I love patterns oh so very much. So this is hypochlorite. This is chlorite. This is chlorate. This is perchlorate. So this gets into a little bit of Latin. Item 8, this is fewer oxygens. This is more. This is even fewer because it's hypo and ite. So hypo and ite always go together. Perchlorate is even more. The per and the ate always go together. So you don't get a flip-flop. So hypo and ite go together. Per and ate go together. That's an always. The other thing that I usually have up my sleeve is, where's the small periodic table? I know I made one. There it is. So I've got a bunch of chlorine things. I'm going to grab my periodic table and look for chlorine. And it's in group 7A. And if I only had chlorine by itself and it was an ion, it would have a -1 charge. And so do all these. The same. So I look for things that can help me. I look for things to hang stuff on. So in a similar way, I can have the sulfates. So this is sulfite. This is sulfate. And if my sulfur had a charge, it would, and if it was sulfide, it would have a -2 charge. This can also be done for my phosphates. So phosphite and phosphate. And phosphite. And if I had phosphide, it would also have a -3 charge. Right here. Boom. So there are patterns. So I think the person in the chat also asked, would I memorize them in that table order? No, actually I would not, because going back to my chlorine examples, the textbook puts them in alphabetical order. So since they're in alphabetical order in your book, chlorite and chlorate are together, and then it skips a whole bunch, and then there's hypo, and it skips some more, and then there's the per. So your book doesn't put them in element order, which I think is a mistake. But that's the way your book does it. And on one hand, I get it, because you have to pick something. You have to pick something. There are also other things that can kind of help out. Let me make sure that this is on the list so I don't give you guys something extra. Yay, it is on the list. Okay, good. So there's also one that is called, so it is HPO4 -2. It is called hydrogen phosphate. So what has happened here is a hydrogen got added onto a phosphate, since we've already drawn this eraser. No problem with that. So when you add that hydrogen, that is going to change the charge, because this is essentially like adding a positive hydrogen ion to phosphate. So if you know what phosphate is, hydrogen phosphate is adding a hydrogen to phosphate. So the charge does change, but the number of oxygens stays the same, and you're just basically changing the charge because you've essentially added an H plus to it. So what I usually do is I look for patterns to help explain things. The hard thing is that once you find a pattern, there's always something that breaks it, or something that just doesn't fit at all. So we did all these things where all the charges do match. Nitrogen hangs out right above phosphorus. So there's all my phosphorus ones. Here is nitrite with a -1 charge. Here is nitrate with a -1 charge. So my nitrogens don't match that at all. So the phosphorus and sulfur and chlorine kind of all play by the rule of what charge would it have if it was an individual element, but nitrate doesn't. Carbonate doesn't. Also, what the heck are you going to do with azide? I mean, look at it. It's so weird. So honestly, when I learned polyatomic ions, I used flashcards, index cards that you wrote on, and you put the formula on one side and the name on the back, and you just carried them around with you until they were stuck in your head. But again, I would start off with patterns. And then the other thing, honest to goodness, y'all, is Google how to memorize polyatomic ions. There's a song, apparently. There's YouTube things. There's all this stuff. There's a whole Reddit thread. I'm not clicking on that right now. Videos, tricks, chemistry stacks, Socratic, Quora, songs, Quizlets, how to remember them. So while yes, we are asking you to do this, it is a plague that happens to many chemistry students in both high school and college. So there is a lot of support to be had for this. That's part of why I went ahead and took the time to answer the question, is because frankly, I think the best thing to do is to keep asking the question and see what answers you get. See what people tell you, see what tricks they have, and see which one resonates with you the most. Because at the end of the day, you just have to figure out what works for you. Okay, so we talked about tips, we talked about memorized polyatomic ions, we talked about example, mostly because I already did one to start off with. But honestly, for exam examples, so many of these you can do. If we can ask you a question about a compound, why not make it a polyatomic ion? If we want to ask you about formula mass or percent composition, why not ask for the percent composition in phosphoric acid, all in words? Why not? It's what you're responsible for. You can sure do it. So we could write almost every calculation question as a polyatomic ion question if we wanted to. It's doable. Let me go ahead and answer this. Empirical exceptions, mercury 1, and I think peroxide. So hanging out in your polyatomic ions, actually, are a couple of things. One of them is mercury 1. Looks like this. This is mercury 1. Trying to figure out they're going to come. Oh, that's not mercury. Up. That's Hg. Hg. So that's mercury 1, and then the other one I believe is peroxide. So I think the question about this was particularly with empirical formulas. So whenever we talk about empirical formulas, so let me just do C2H2. So this is a molecular formula. And the empirical would just be CH. An empirical formula is one where you have the lowest ratio of each of the elements that we're talking about. So the thing is that whenever we're talking about empirical formulas, honestly, even though I just gave a molecular and an empirical example, molecular ones are honestly the time where if we're asking you about this, we're asking you basically for a definition. Because the whole reason why we have molecular formulas at all is because they tell you how many elements there actually are there. And we usually need that information. We usually need to know how many elements are actually there. So if we're asking you for the empirical formula, you're just going to go ahead and give us the lowest one and do the division, because we're asking you essentially about the definition of empirical versus molecular. There is this oddity, though, where mercury 1 is one where there's basically two metals that always travel together. So that would actually be a time where what you very well might see is something that looks like an exception where you would have an ionic compound that might not be following the rule that elements need to be empirical. So, but basically it would be like a little hidden trick. So for example, this as written is mercury 1 peroxide. That is what this is. So this is correct for an ionic naming. It's just strange because usually for metals, we don't usually see subscripts repeated like that. So for example, if I wanted to write magnesium oxide, that comes from magnesium 2+ and oxygen 2-. And I would absolutely just put MgO for that because they both have the same charge. But whenever you're dealing with peroxide or mercury 1, if you're writing that from scratch, you do have to go ahead and keep the subscript in there. So hopefully that answers that question. If we're asking about molecular versus empirical, just do it. However, if you have mercury 1 is always Hg2, always. If you're asking about peroxide is always O2, always. So actually, I know it will look weird, but let's say we were doing 10 for peroxide. So that's 10 with a +4 charge and then peroxide with a -2 charge. You would actually write it out like this, because I have to have 2 peroxide units to balance the +4 of 10. So these can get a little bit strange. These can in fact get a little bit strange. But you might also notice that I don't have to do 2 10s and 4 peroxides, right? So I can still keep that empirical idea, but I'm still going to keep my peroxides together to demonstrate that that's a polyatomic ion. Okay, so I know I have not answered everything yet, but it's been about a half an hour. So let me go ahead and see if there's more questions in the chat for now. Questions in the chat?
Yes, ma'am, there is.
All right.
Can you explain molecular geometry when drawing Lewis structures? When drawing Lewis structures, do you draw all structures like PO43? Do we draw the first structure with no double bond? Can you explain how to determine the number of ammonia molecules in 38.0 grams of ammonia? The proctor, oh, this is about the proctors. Proctors made you look at them multiple times during the exam. Is that normal? During the ALEKS test for this unit, They tested us on polyatomic ions like BRO, IO3, and etc. Um, do we need to know these ions or only the ones on the list given to us? And then other proctors, it wasn't you. I was in Hoblitzal 2.402 with 3 proctors and a professor. Uh, when it when is it asked to draw a Lewis structure? Do we have to worry about formal charge like the one you did? Give me just 1 second. There we go. How can you find the radius of an atom slash ion? You can go over Lewis structures with the octet rule. Would it be a weird idea to write down all the ions we remember on scratch paper once we get to our exam? And can you go over how to recognize when to use Roman numerals when naming compounds? And I believe that is everything.
Okay. So to answer the proctor question, is it normal for the proctor to have the proctors look at you multiple times? So in a perfect world, the proctors would come around once to check your IDs, and that would be it in a perfect world. So in a perfect world, you would have the proctors would be divided up such that you had to, so that they would check your IDs. And as they check your IDs, everybody does it differently. So, and again, a lot of our proctors are brand new, so odds are good they're going to look at your ID and they want to look at you, because to make sure that you match the ID. Also, what they should be doing is making sure that your ID matches your face and that your ID also matches your Scantron. So that actually might be why they came around again. Is that's actually the thing that takes me the longest if I'm personally doing it, is I will sometimes get stuck standing in a row, either trying to wait or trying to find time that I can double check that the student's ID matches their Scantron. So that might have been what they were doing. Yeah, I'll make a note of that and see what I can do, because we'll just see what I can do. When you get better at looking at people, I become obsessed with people's noses and their eyebrows, and the space between their eyes. Which means it can't always, because some of y'all, when you do your exams, you're like way down here, but a lot of y'all, most of y'all, are at an angle such that I can still see the bridge of your nose in your eyes. And that's usually enough for me to be like, yeah, that's probably you. Because a number of y'all grow facial hair in between your in between your comment card, and when I'm looking at your comment card. So, or you color your hair, and so like the comment card you had brown hair and now you have like pink hair, and I think that's great. But your hair does not help me identify you at all. But yeah, I made a note. I'll see what I can do about that. So the question is, Alex had additional polyatomic ions. Do we need to know those? Here's the game. I always try to ask my colleagues what the answer to that question is to see if we all agree. Right now, I'm going to tell you that the answer is yes. But we're going to talk about why I think that the answer is yes. Also, I have to go over this with my class because I didn't do it yet. I had polyatomic ions, but I was going to just double check. So here's the reason why we think as a teaching team that y'all could totally do ones with bromine or iodine without a problem. Because they fit the pattern. This is hypobromite. This is bromite. This is bromate. This is perbromate. I could do it with iodine too. And it's the same thing. So I'm going to tell you that yes, you are responsible for those. They were in Alex. I am going to be revamping my notes a little bit to make sure that I put them in there. But you absolutely can name them because you're responsible for chlorates, and they are the same as the chlorates. You just swap out the element and you just swap out the element name. Otherwise, they're identical. They're identical in charge, they're identical in oxygens. They are the same. They're also all halogens. So they go, oh, I already did that, darn. They absolutely go on top of each other on the periodic table. Chlorine, bromine, iodine, all go together. So I'm going to go ahead and say yes, that you do have to know those. You can ask your instructor and see if they give you a different answer, but I'm going to go with yes. Okay. I got a lot of questions about radius, so let's talk about ionic radius and give us something a little bit different to talk about. So, couple things. One, what do I want to grab? Let's grab argon. So argon, when it's neutral, has 18 electrons. It also has 18 protons. Next to it, chlorine. If this is the chloride anion, because it wants to look like argon, it would also have 18 electrons, but it would only have 17 protons. So first of all, this is what we refer to as being isoelectronic. It has the same number of electrons. So isoelectronic means it just has the same number of electrons. That's all that means. Then what you might notice as far as size goes is argon's going to have some size, whatever that is. It's to the right, so it'll be kind of small. Then chlorine, notice it has the exact same number of electrons, but it's trying to hang on to it with only 17 protons. So if argon has 18 electrons held on with a positive charge of 18 and you have a certain size, when you go to chlorine, this is going to be larger than argon because it's trying to hold on to an extra electron with less positive charge. So that chlorine should be larger than argon. That chlorine is also going to be larger than a neutral chlorine, which technically should have been a little bit larger than the argon because of atomic radius. But a negative chlorine is going to be larger than both of them. So it is fairly significantly larger. But in that regard, we could come over here and look at a sulfide anion with a -2 charge, 18 electrons, but only 16 protons. This thing should be even larger than the chloride ion. So I do usually, when I'm doing ranking of isoelectronic to noble gases or doing rankings of size, I will usually go ahead and grab where they are on the periodic table, but I'll also go ahead and look at their ratio of protons to electrons, because essentially the fewer protons they have to hang on to the same number of electrons, the larger that they are. And likewise, if you flip that, and let's grab potassium and calcium. Potassium, 19 protons hanging on to 18 electrons. This thing's going to be really small, right? And it's going to be smaller than the argon because, again, argon was hanging on to 18 electrons with 18 protons. So it should be smaller. We can put calcium in here. If it also has 18 electrons, 20 protons, this thing should get way smaller because you've got 20 protons hanging on to 18 electrons. That ratio of the positive charge in the nucleus to the number of negative things in its electron cloud will tell you if it gets bigger or smaller, and bigger or smaller than what. So you guys should be able to rank those all together. But keep in mind that these have got to go in an order that you can figure out with a periodic table alone. So for those of you that I know are going to be like, ooh, well, let's pick something like fluorine, which is going to be larger, but then let's pick something like cesium, which is going to get smaller, but it's bigger because it's no. We have to go in an order that makes sense. So we can definitely do multiple things that are smaller, but then we have to do all things that should be smaller. So what I mean by that is we could do like, so right now, because everything has 18 electrons that I've done so far. So right now, I could absolutely rank everything I have. Calcium 2+ is the smallest because it's got the smallest positive charge, then potassium, then argon, then my charges that get bigger, then the chloride anion, then the sulfide anion. So I can absolutely rank everything I have. All of these so far have 18 protons. If I want to add to this list, if I want to add to this and I want to go outside of the range, if I want to go bigger, I'm going to either go larger in charge or I'm going to go down the periodic table, but I'm not going to go up, and we'll go down. So if I wanted something, so I could absolutely add selenium to this because it's one slot down from sulfur, so it should be larger because it has more shells, a higher value of N. So I could absolutely stick that on here, and that's fine because I can directly compare the two largest things to each other. Similarly, I left off with calcium. If I want to go smaller, I could go up. So I could hit magnesium or the magnesium cation. So keep in mind that when we're ranking, you have to be able to rank them with a periodic table and only with a periodic table. I know y'all sometimes get really creative in how you can come up with things, but overall, it has to be something that works together. So if it's going to be a bunch of positive things, then we can do multiple rows. They don't actually all have to be isoelectronic, but they have to go in a way where you can predict it using only a periodic table. So that's where that little bit of atomic radius comes back, because knowing that the magnesium cation is smaller than the calcium cation is all back from atomic radius. When we would do things and look at the periodic table and say that as you go down, things got bigger because you got larger values of N. So higher on the periodic table, smaller elements, lower on the periodic table, larger elements because of the values of N. So that's that part that usually comes back that really was just the atomic radius trend. So yes, the atomic radius trend is still valuable and useful when doing ionic radius, but you might notice that the thing that is controlling this the most is the charges. So if you have differences in charges, that's going to be the factor you're going to focus on the most. Then if you have to decide otherwise, it is still good to keep a look at where they are on the periodic table as well. But we have a tendency to focus on charge when we can. And if we have to look at the size, then we will. Okay. Feel like I'm a little bit of everywhere. Okay. So radius trend, we did that. Isoelectronic, we did that. Bond order, I'm actually going to say we did bond order because even though it was way up here, we actually did bond order when we were looking at all the different phosphorus ideas. So we did actually do bond order when we looked at the fact that the phosphate anion has resonance, and we can essentially look at the bonds for bond order. The simplest way to do bond order is that a single bond counts as 1, and a double bond counts as 2, and a triple bond counts as 3. So it does mean that you could do simpler examples. So here's carbon dioxide, and the carbon-oxygen bond, because there's only double bonds here, this has a bond order of 2 for the carbon-oxygen bond. And we could still do that math if you'd like, because there's 2 double bonds, so they each have a bond order of 2, and then there's a grand total of 2 bonds in here, so that gets you 2, 4 over 2, or 2. It's just we have a tendency to ask about bond order in an application to resonance, is where that usually pops up. So there is that. Okay, bond order. So I know some people are asking about nomenclature in general. Naming covalent compounds. So when to use Roman numerals, things like that. And that's all naming. So I assume it's in the book still. So your book actually has another thing that I like, which is this lovely little flow chart. So if it's molecular, we're going to use prefixes. If it's ionic, we don't need prefixes. So there is this kind of handy dandy chart hanging out from your textbook to help you with naming. So one of the other things that you will have is a periodic table. So keep in mind, as we're looking at the periodic table, and I know the metalloids get weird, but in general, you have a whole bunch, whoa, more than that, and you got to include carbon. There we go. I want the eraser. There you go. So these guys are nonmetals. So if you have all nonmetals, this is going to be covalent. There is an exception to this because there's an exception to just about everything. So therefore, if you have this guy, this is carbon dioxide. You got to tell me how many oxygens are in there. Technically, even though the carbon isn't mentioned, it's assumed that it's 1. So if it's more than 1, you got to tell me about that. So if I was trying to name, this is not how you name it, but for kicks and giggles, so this would be dicarbon dihydrogen, because there's 2 of each. For those of you that are upset about this, it's also called acetylene. So it's got a different name, but that's an organic name. But we would call that dihydrogen dioxygen. Dioxide. I was like, it still seems a little weird. Dihydride. Ugh. Dicarbon dihydride. Great. Terrible. Strange. It's acetylene. That's fine. But the notion is that things are going to end in IDE. That's going to happen. You're going to have 1. If it's not told to you, then it's 1. There are a list of Greek prefixes to memorize. You're memorizing 1 through 10. But in Greek, you've probably seen a startling large number of these before. Mono, di, tri, tetra, penta, hexa, hepta, octa, nona, deca. I mentioned earlier that I've been teaching this class for over a decade. Decade's 10 years, deca. where it comes from. So hopefully that's helpful. So therefore, if that's covalent, last thing needs to end in IDE, you got to tell me how many of them there are, because there's no charges to help us out, unless we do need to do the exception. The exception is things like this, where this is all nonmetals, but this is actually a polyatomic ion. So this is actually ammonium chloride. There are still no prefixes here because this is actually ionic, because this is the ammonium ion and a chloride anion, and that's why there's no prefixes here. So I mentioned, hey, if it's all covalent, you should be using prefixes unless it's one of the exceptions. And really, this is not technically an exception because it's actually ionic compounds, because that ammonium ion is positive and that chloride anion is negative. And this thing is actually held together with positive and negative charges. But it does have all nonmetals. It is all nonmetals, which, you know, I get it. Then the people were asking about Roman numerals and not Roman numerals. So there are, so ionic compounds are metals and nonmetals, again, unless it's ammonium. Are ionic. So, and you've got two types of metals. You have metals that have always the same charge, or you have ones that have variable charges. So if it always has the same charge, you just get to name it. Magnesium chloride. Totally correct. Sodium chloride. Totally correct. Because when you look at a periodic table, group 1A is always +1, group 2A is always +2, always, all the time. So you don't have to tell me what those charges are on anything in group 1A or anything in group 2A, because they always have the same charge. You don't have to tell me, I know. Then there's a couple other things that always have the same charge. Aren't you excited? But they are in places. Let's do that in green for funsies. Green. So silver is always +1. Zinc and cadmium are always +2. And aluminum is always +3. This is in your textbook. This is in that chart. This is in a couple of different places. So you guys should be able to find these. So aluminum chloride, silver nitrate, zinc oxide, no Roman numerals. You don't need them. They only have the same charge. They always have the same charge. No need to specify. There's a lot of green elements. Green are the metals. It's a lot of green elements though, especially in like the D block or in the P block that we didn't talk about. All of those need Roman numerals. You're going to tell me what that charge is. I don't know. Manganese has a whole bunch of options. Iron's got 2 options. You got to tell me what they are. So if you have this guy or this guy, the one on, so this still doing chloride. It's easy, okay? Chlorine, -1 charge. So the one on the left, since there's 3 chlorines, 3 chloride ions, this tells me that my iron has to be a +3 charge. So this is iron 3 chloride. This one has 2 chloride ions, so it's going to have a +2 iron. So this one is iron 2 chloride. In a perfect world, there is no space between the iron and the Roman numeral, but there is a space. between the chloride. When you handwrite it, you know, you're just doing your best. So you need Roman numerals if the charge can change. If it's so especially transition metals. So if you have an option for the charge, you got to tell me what that charge is. If there's no option for the charge, then we've made you memorize all of those, so you can assume that I've memorized all of those. So hopefully that clears up what's going on with Roman numerals. You can still usually find stuff for this. We haven't used this in a while, but if anybody asks, it's accurate. We just don't do it anymore. This is also called ferric chloride. This is also called ferrous chloride. You don't need to know that. We don't test on these anymore, but they're correct. I've seen a couple of people, I think they might all be international students who happen to know those. So, I mean, they are correct names, but we're going to ask y'all for the Roman numeral version. So one less thing to memorize. Shockingly, we used to make people memorize more things. We've cut it down, believe it or not. I've lost track of my list. Names of compounds. Oh, I did this. Oh, somebody asked. Okay, so we talked about the bromates, the iodates. I've made notes about the proctors. We talked about Roman numerals. We talked about radius of atoms. So somebody asked, do I think it's a good idea to write all the ions on scratch paper? Yeah, I don't know. I know that that's not helping, but the truth is that it would depend on how fast you write. It also depends on if you're going to recreate and write them all down, or if you've got shorthand. Because if you were going to do something, like if you're just going to name me one, basically, if you could do this in like 3 minutes or less, then I'd say it's probably worth your time. If it's going to take you 10 minutes to write out all the polyatomic ions, that's an eighth of all your time. That's not worth it. So it really depends on how fast you are at writing and what kind of shorthand notation you've got. At the end of the day, it's your time. Honestly, what I would probably do if you're worried about polyatomic ions is I would do all the polyatomic ions first. I would go through the exam. I'd look for everything that had a polyatomic ion, and I'd just write it down. I translate it first. Because one of the things that is helpful to know is our exams are all written. They're written by people. They are put in order by a computer. So we use a random number generator to put the questions in order. So there is no thoughtful process behind it. So what that means then is if you wanted to know which polyatomic ions you need, one of the tools you could use is you could flip through the exam, find all the questions that use polyatomic ions or all the questions that do nomenclature, and you just do all the nomenclature first while you still remember it. And then that way, when you're more tired, because in any exam, towards the end of the exam, you get tired. Like that's just the way brains work. You get tired towards the end and you're like, I don't remember anymore. Then do something that you are more comfortable doing while tired. I don't know what that is because everyone's different. And right now, at least 10 people have like different things in their brains of what that might look like. So it's a valid question. It's a good question to think through. I don't know. I don't know the answer. It really depends on how fast you are. Other things I can do kind of quickly. Somebody asked me for molecular geometry. This is chapter 7, which is on exam 3. So I think the way it was phrased was something like, do I know or can I go over? And the short, yes, because I know all of that, but you don't want me to go over any of it because it's all on exam 3. So quick thing. I am well aware that people have access to exams that are earlier than last year. So we post the fall 23 exam, and I'm well aware that y'all can find things that go back farther than that. If you would like, you are more than welcome to take a screenshot of whatever question you're looking at and shoot me an email and be like, Dr. Taylor, is this on our exam? You do have to send me a screenshot though, because that is me doing you a favor, and I am not going to dig back through and find the fall whatever you're looking at exam and figure out which question you're looking at. You got to send me a screenshot or a topic and ask me. I'm not gonna go dig through exams for you. I will look at something you send me and answer your question. I will totally do that, no problem. But yeah, I pretty much promise that that person's got old prior to COVID exams. You're going 2019 and earlier, my friend. Back when molecular geometry used to be on the second exam. And the second exam I think came later in the semester too. So I'm not going over that because that's not on this exam. So people were asking questions back on the phosphate example. So part of the game with the phosphate example is it depends on what the question asks. If the question says to, like, if resonance, draw all resonance structures, then you have to draw all the resonance structures. In which case there's 1, 2, 3, 4 of them, and you have to draw all 4. Sometimes the question just asks you how many there are, so sometimes the question is how many, in which case it is the number 4. So I definitely understand the question as far as do we have to draw all of those? Read the question, read the instructions, and that should help you out with what that is. But a lot of times it'll say something like, if resonance is present, then draw all valid Lewis structure, or draw all resonance structures after you've optimized for formal charge. So just realize that that question comes in different formats, and so you should be prepared for either one. So yes, you might have to draw all of them, but maybe not. Maybe not. I think it's time. And I think the other question was like, if we were drawing, would we draw, including the first one where there was no double bond? If we're asking you to draw a Lewis structure, then you should optimize for formal charge. So we usually will ask you to draw the best Lewis structure. And the best Lewis structure means that you've optimized for formal charge. So way back here in this example, when I first started drawing it, I drew one that had all single bonds. This is a valid Lewis structure, but this is not the best Lewis structure. So what you would actually do next is you would go ahead and optimize for formal charge first, and then tell me this is my structure, and then start drawing resonance structures if applicable. So just keep in mind, you're going to optimize, you're going to follow, where did they go? I wrote it down. This, draw the valid Lewis structures, check the octets, check formal charge. So this step here is where you know that it's the best Lewis structure. And this is typically what we ask for. I say typically because sometimes I think we forget to put the word best in there, but that's what we're looking for. We're looking for the best Lewis structure. What is the best Lewis structure? Includes checking for formal charge. So 6:15. You know what? Just in case. So let's go ahead and take another round of questions.
Okay, so what do we need to review the most? Would Roman numerals and prefixes be needed when naming a covalent bond only? Also, would all ionic bonds end in "ide"? Are there any exceptions between those two? Let's see. Are we still going to get the formula sheet in this exam because most of the equations are not useful for these units? And I think that's it.
Okay. So prefixes are for covalent compounds. Roman numerals are going to be for ionic compounds. You should not be using those together. They do not belong in the same place at all. As far as do all ionic compounds end in "ide," this one actually depends because this is iron 3 phosphate. So your polyatomic ions do not end in "ide," IDE, but that is an ionic compound. So again, I know that I'm being a little bit finicky even when I'm answering these, but it's just to keep in mind because I know you're looking for always. Now, if this was that, then this is iron 3 phosphide, and then yes, that does end in IDE. So if it's just the two elements, yes, but if it's a polyatomic ion, you're going to name the polyatomic ion. Formula sheet, yes, it's going to be the same or almost the same. I need to double check. Essentially, we're lazy, and you might need Avogadro's number still. So we'll just give you the whole thing. We only add equations onto things. We won't ever take them away. So you'll be on the last exam, and we'll be doing like gas law stuff, and you'll still have the wavelength equation. You won't need it. You don't need wavelength to do gases, but you'll have it. You won't need it, but you'll have it. So yeah, the formula sheet, we only add things to the formula sheet. We never take things away. So yes, you'll still have it. You'll definitely still have that one. What do I think you need to review the most? So this is where, I don't know if you know this, but every instructor chose a different path through all of this material. We did, which frankly, I love at this point, only because the only other option is to make us all do it the same, and I don't want to. I have spent time trying to do things the same way as Dr. Diekman and Dr. Seibert, and I can't. Or at least I'm not as well as when I shuffle things around. So this is what I did. So this is the hard thing. My class could probably use a review of Lewis structures because we just learned it, and they therefore need to practice it some more because we've been doing Lewis structures for less time. My class also used to go back and look at the calculations again, because they haven't seen them now in like a week or 2 weeks, because I did all the calculations in the very first week after exam 1. So my students haven't thought about calculations in a while. The other thing, as far as what to review the most, the hard thing is that there's always a set of things that we touched on and we talked about, but either it's been a while or there just weren't that many examples of, which honestly at this point is everything out of chapter 4 that we did, which granted, we talked about some of that tonight. So I honestly don't know what you need to review the most. Usually this is stuff that was earlier. I'll go ahead and put Lewis structures just because those are really important. Or things that it's one topic and go. So I think about this, things like metal cations. I'll give you an example. What do I mean by one topic and go? That doesn't even make any sense. Let's look at one of these. This one. Transition metals and valence electrons. This is what I mean by that. This in my notes is one slide. Now granted, technically, this was also a slide very similar to it for the first exam, but this is one slide where it says electrons are always lost with the highest in value first. That we're going to lose valence electrons, we're going to lose out of the highest value of N. So when we're looking at iron, you're going to lose those 2 4s electrons first before anything else. This is one slide. This is also polyatomic, oh, not polyatomic. This is also electron configuration of ions. And electron configuration of ions is one of the topics. So that is like out of your textbook, like a big, like your textbook spends time on this. So I would be okay with that. We have already talked about ions and sizes, and that's good. We've talked about isoelectronic to a noble gas. I think you guys actually asked questions about the stuff that's in chapter 4 already. Information we still need. Did I ever fix this? I did finally fix this slide. Shoot. Need to repost. So yeah. Hopefully that is helpful. Some things to review. Okay. 8 minutes. 8 minutes. What can I do in 8 minutes? I can do this question. How I'm not entirely sure what this question is. Let's pretend that this question reads how many hydrogen actually with this, how many ammonia molecules are there in 38 grams? Oh, there went my AirPods. They do really well for about an hour and a half. And then after that, it's just the roll of the dice. How long will it last? How long will it last? Okay. So, I got enough time for this. So, here's another time where it's all in words. So, ammonia is in H3. Just to make your life worse, I'm so sorry about this. I did not name this. This is ammonium. This is ammonia. Ammonia, 3 hydrogens. Ammonium, 4 hydrogens and a positive sign. But we're doing ammonia. So how many ammonia molecules are there in 38 grams of ammonia? I need a periodic table. Because we're finally going to do some math. A reminder, I will do a follow-up video with some more examples. So ammonia has 1 nitrogen at 14.01 grams plus 3 hydrogens at 1.008 grams each means that this whole thing, write it out. That's me talking to myself. Is 17.034 grams. Oh, all these are grams per mole. Grams per mole. Grams per mole. So this is my molar mass. So I have molar mass to go from grams to moles. I have grams. I want molecules. So this is where I would also grab off the potentially useful information page. This number, because this number is going to tell me how many molecules are in a mole. Now, math time. I don't know why I needed to wave my hands in the air like that, but I did. So, 38 grams of ammonia. We have already found that there are 17.034 grams in 1 mole of ammonia. And then in 1 mole of ammonia, there are 6.022 times 10 to the 23rd molecules. We are going to multiply across the top. Divide by the bottom. And in general, grams are always bigger than moles. So as you start with grams and go to moles, your number ought to get smaller. Then when you go to molecules, this should get a lot bigger. If we're asking about number of molecules, there should be some positive exponents on that somewhere. So I get a grand total of 1.34 times 10 to the 24th molecules. So that should look relatively familiar because there were some questions that we asked on the first exam that had a very similar feel. We were using atoms instead of molecules, but a very similar idea. But on this one, we can still go to atoms because we have 3 hydrogen atoms for every mole of ammonia. So one of the things that we could do is if we wanted to know how many hydrogen atoms are in 38 grams of ammonia, all we have to do is take the last number we had and copy it correctly. And then we can say that in every 1 ammonia, there's 3 hydrogens. And we just multiply that by 3. And now we have 4.03 times 10 to the 24th hydrogen atoms. So that's another thing we can do. Is we can go ahead and we can still go to the same things that we did before, only now going ahead and using the idea that we've got molecules. So we've got multiple hydrogens attached to that nitrogen in 1 molecule of ammonia. So we could still think about breaking that apart and be like, so how many hydrogen atoms are along for the ride if you've got that many molecules? Now we could break it apart. So it's another option. So I know I did not finish all of the topics, and that's okay. I will make a follow-up video and send it along. So if there are other questions that I did not get to that got dropped in the chat, the lovely folks will send me an email because for equations on the exam, there's usually 3 different ones I do. We did one of them, which is the moles and molecules as well as the mass one. But I would highly encourage y'all to take a look at the fall 23 exam if you haven't already, because that'll have a pretty good representation of the different mathematical options, not necessarily all of them, but that'll have a pretty good one on there. We didn't get to electronegativity trends. I'll draw another Lewis structure, ranking by percent ionic character. Formula mass, hey, we did one of those. We could spend a little more time about ionic bonding. We did molecule nomenclature, though. We did not do a percent composition. That's another one of the
math ones that we can do. Doing more Lewis structures with octets. Okay. And formal charge. So a couple more Lewis structure examples seem like it would help y'all out. And then doing probably 2 main math examples that do percent composition forwards and percent composition backwards and electronegativity. Okay. Not bad. Not bad at all. Okay. Well, it is 6:30, so it is time to say goodnight.
Awesome. Thank you so much. We go ahead and close this out if there's no more questions or anything.